Welcome everyone. This is the end-to-end reverse engineering solutions panel. We will be here for a quick 20 minutes. My name's Kathy Lancaster and I'll be the moderator. I'm going to be going off in just a second. Just so everyone knows, we are in a Zoom webinar and not a meeting. What that means is for any questions, you'll want to click on that Q&A button at the bottom toolbar to post your questions. I'll be moderating those questions and feeding them to our panelists. And I'm going to hand it over to Chris right now to start introductions.
Hi, my name's Chris Chimera. I'm part of the Connex Agile Additive Manufacturing and Logistics System team, also known as CAAMLS or CAMLS. That solution was selected to the Agile Additive Manufacturing and Reengineering Challenge Showcase. I also serve as a dedicated advisor to Millebot, a manufacturing startup that is utilizing the standard ISO shipping container to bring integrated mobile manufacturing and logistics machines to the market in agile additive manufacturing. For the last few years, I have served as a consultant and advisor to lean startups in manufacturing, insurance, and education. And I'll talk a little bit more about the Connex Agile Additive Manufacturing and Logistics System, or CAML solution. It is a patented mobile machine platform utilizing the intermodal shipping container to produce very large format, multi-material 3D printers and additive, subtractive CNC cutters, and 3D scanners in independent or all-in-one machine configurations. As foundational extreme service hardware, the platform is extensible, and modular to add and recombine new third-party OEM technologies to enhance and or change functionality over time. These unique capabilities can give the United States Air Force and the DoD more broadly, in theater, on demand, and anywhere, advanced manufacturing and reverse engineering capabilities that are impossible with other solutions currently. With the Connex Agile Additive Manufacturing and Logistics System, the shipping container becomes the machine. The factory and logistics are all in one. The system is now available to produce and ship in many configurations.
Great, thanks so much. Mingu, why don't we go to you next?
Thank you, Kathy. My name is Mingu Kang. I'm the CEO of ARIS Technology. ARIS Technology automates 3D measurement using robotics and artificial intelligence. We basically integrate 3D sensors, robotic devices, and then image processing tools into a integrated seamless system that can collect high resolution, high accuracy 3D scan data and use it for primarily metrology, which will be inspection and or reverse engineering. Our proposal was created by teaming up with other experts in additive manufacturing and subtractive manufacturing downstream once reverse engineering happens, and also precursor to that, evaluating the current problem set in reverse engineering and making a decision model. So we call this proposal end-to-end reverse engineering solution, particularly using mixed reality. So why that is because ARIS's currently existing systems that can capture and process three-dimensional data even for lower volume, high mix environments is a very good fit for reverse engineering. However, actually automating reverse engineering is very tough because manual expertise is required. So for that process, we are proposing sort of two directions. This one direction is basically using mixed reality to help users overlay 2D and 3D data together, whether it's a scan data and 2D drawings as such, or OCR on that matter, to advance data collection of human interaction with the robots, sensors, and such to eventually automate reverse engineering in the long term. In the short term, by having a dedicated metrology lab that can perform such reverse engineering, creating the data package of 3D scan data, 2D drawings, and PMI data. Thank you very much.
Thanks, Mingu. Tim, you're up.
Okay. Good afternoon, everybody. My name is Tim Bell. I am the head of additive manufacturing for Siemens Digital Industries. Today, I'm representing one of our business units within Digital Industries, What do you say about Siemens? Siemens is a massive entity, founded in 1847. We operate in just about every country in the world. We're 380,000 employees. Siemens operates as 6 individual operating companies, being Digital Industries, Siemens Gamesa, Siemens Energy, Mobility, Smart Infrastructure, and Health and Ears. Today, we're going to discuss the Digital Industries division. And inside of that division, it's broken up into software, factory automation, motion control, and process automation. In the additive manufacturing world, Siemens has been a user for many, many years, and has now in the last few years decided to take their learnings and share the Kool-Aid with the rest of the world, if you will. And I think most of you, if you're in the manufacturing industry, you're very familiar with Siemens from a software perspective, whether it be from Teamcenter or NX, some of our simulation tools, Star CCM Plus, a lot of other features and tools that we have to offer automation and your software packages. On top of that, being a leader in motion control and factory automation, we also support all of the OEMs and machine builders, custom machine usage, whether it be robotic driven, 3D printing, automation, whatever it might be. We more than likely have the tools. Quite often, and when I talk to groups of people, I say, Siemens is that elephant in the room. We have that full end-to-end digital thread. We're the only company in the world that can actually provide a complete nose-to-tail digital solution, especially around reverse engineering and additive manufacturing. My background is 35 years now in manufacturing, the first 20 in traditional, but the last 17 years I've been in additive manufacturing, mostly in metals. I'm one of the original members of Morris Technologies before General Electric Aviation purchased them. So I've kind of seen the evolution of additive, and I can tell you today it's an exciting place to be in, and I appreciate being here.
Great, thanks so much, Tim. So I don't see any questions yet in our Q&A. Oh, here we go. First one, we are a small mechanical reverse engineering company specializing in the creation of the 3D data and the subsequent ID and qualification of new sources of manufacture. All of the Siemens presentations that I have seen do not include how the data is actually created. They always start at the point of, quote, post, unquote, reverse engineering.
Sure, I'd love to address that, Scott. If you think about Siemens as a company, we don't produce any of the equipment that would actually collect the data for reverse engineering, whether it be a scanning system, whether it be structured light, white light, blue light, CMM, however the data is collected. Since we don't play in that space, the only space that we can start our presentations from is once that point cloud's been collected, what do you do with it from there? And I think that you would find within the NX platform and the convergent modeling, you'd find that it's probably the most well suited to go from that point forward. Hopefully I answered that question well.
Great, thanks, Tim. Since that was a Siemens specific question, I'm one of our another question, hopefully open it up a little more, maybe spark some ideas for our attendees. So if each of you could maybe go through this question. How is your solution and enabling technology for end-to-end re-engineering, and what subcomponent does it address? Chris, do you want to start with that?
Sure. Well, as I previously explained, right. It's a, the Camels platform that's being utilized by Millebot is it's foundational, basically foundational hardware operating platform technology, meaning it's the hardware. And that can enable the integration of Industry 4.0 solutions, anything from Industry, I guess, 2.0 at this point to Industry 4.0 solutions, to deliver those advanced manufacturing and re-engineering capabilities. And one of the real unique features is that it can go from a controlled lab environment to extreme outdoor environment in theater deployment, being a self-contained unit. So, and I can show you behind me, right here is this is a development machine we have a picture of. It has all the visual swag in it. You can order that optionally. So we have here a 4-rail H gantry. You can see on our website, we have also some production machines that we've moved to a 2-rail up on the top and just a gantry that comes from the ceiling that creates fewer issues. We use this as a test bed early on. So it's a place where it's like Tim's solution and other solutions in metrology and scanning, and in addition, all the remote, Industry 4.0 digital twin technology can interface with that. But in the end, you need something that's going to produce and or analyze something that's in physical space. So that's really where we see we're an integrator, and so we're the self-contained platform that you hang pretty much everything that can be integrated onto it. So you can go from, we have basically solutions in scanning all the way to subtractive, which people frequently are, even in this agile additive manufacturing environment, is still a frequently essential, almost usually always essential component of post-processing. So to just create a pure additive solution, it doesn't generally meet the customer's needs.
Great, thanks. And I'm going to ask Mingu if there's anything you wanted to add from your introduction, and I think there's something, sort of a question, following Tim's initial question. It says, thanks, Tim. You clarified what I was asking. Sounds like Mingu is doing this as well in terms of true manual reverse engineering metrology while trying to automate the process. So Mingu, do you want to respond to that?
All right, definitely. So I'll try to kind of sum those questions all together. So kind of the space that ARIS is playing is, think of it as in the process of remanufacturing. Our experience typically has been in mission critical components that typically doesn't get additively manufactured at this point for flightworthiness. So in that case, let's say we're machining something, our client would basically use our technology to create the data that Scott was mentioning. And then we use some automation as much as we can to, as an example, take it to a good solid mesh and processing the data further. But once that happens, still there's a manual component of turning that into manufacturable CAD, not just the STL file. But once that is done, a lot of times there's a good communication between the data that we can create and then, as an example, NX for producing parts. But once that is done, then we actually get that data out and we can use the same program for quality control in case you're using that design against the part that has been machined, right? So where ARIS plays a role in, or this proposal plays a role in, be highly relevant to actually collecting the data and learning from that data into a decision of manufacturing or a decision of quality.
Great, thank you. Another question here, just to keep us moving. And just so everyone knows, we have about 6 minutes left. What are some good examples of end products produced with the digital thread? Who wants to take that?
I can take that. A good example within the additive manufacturing world, if you want to talk complete end-to-end digital thread, is we have OEM manufacturers of the actual 3D printers or the industrial additive manufacturing machines who've actually designed the machine using NX, using Teamcenter for PLM. They've actually done virtual commissioning of the machine, meaning taking the kinematics and the physics models, running them in Technomatics product within the PLM packages. Also doing PLC simulation, and then once they've actually commissioned the machine, then the components were designed with the same software platform, they were simulated with the same software platform, and then the output to the machine was also again linked to the digital thread through the Siemens motion control. And at the very end of the day, we were able to collect data from the machine using the MindSphere platform, which also known as the Industrial Internet of Things, and feed that data back into the design data. So that's a quick answer to your question. With only having a few minutes left, I didn't want to take all of that, but I'd be more than happy to talk about complete digital thread with anyone offline at another time.
And does anyone have anything else to add? Chris or Mingu?
This is still at a research level, and it's kind of the same dilemma as solving reverse engineering. But we're working on currently being able to create a quality to design loop for additive, because at least in additive perspective, for some of the parts that we can make, it can be done in the form of solid mesh. So even though reverse engineering may not be perfected to the level of parametric data, we can use high quality scan data to potentially make a better part. So that's an area where we are looking deeply into. And if anybody is interested in partnering or have questions on that, we'd be happy to discuss.
Sounds good. Chris, anything?
We should move on to the next questions. That would be good.
Okay.
It's a little time.
Okay. And I think we're still good. Knowing the difficulty of securing cyber physical systems, what are your thoughts about hardening these systems to prevent problems in a cyber contested environment?
It's more of
it's a tough question.
Yeah, I mean, there's many facets of that. Really quick, I can talk about, there's a lot of discussion about side channel being a methodology of obtaining build or manufacturing data from a machine based on some attributes of the machine that you could easily obtain by walking past it. Siemens is working very closely on trying to build systems within our motion control platforms to prevent side channel from a cyber contested environment.
Okay, so we have just a few minutes left. Panelists, if you can see Scott's questions, they seem, oh, I think we can go to that. Are any of you aware of almost automated 2D to 3D tools?
I can share some perspective on that. My personal experience, it doesn't really exist for complex Air Force components is my personal perspective. However, there are definitely geometric magic you can do to turn simple 2D drawings that is well-defined into 3D files. In reality, for this challenge, I have a hard time believing that's going to be the case. So that's why the concept of using mixed reality to provide the insight and manipulability to perform reverse engineering using 2D on top of 3D as a proposal. So short answer, I would say it exists, but it doesn't really exist.
Okay, so we have just a couple of minutes left. I think we can have time for this one last question, and then I think we'll have to wrap it up. We've been manufacturing patient-specific orthopedic devices from CT scan through design, PBF, scan, inspect 3,000 times. FDA approved worldwide distribution. I think that this is a case of end-to-end reverse engineering. Thoughts?
I would call it specific engineering more than reverse. Having been involved with creating orthopedic implants from MRI data in the past, it's more specific, and unfortunately, I haven't seen any good automated tools for that.
I would also agree to that because you can generate something we can call digital twin, but making it manufacturable typically is a different problem.
Yep.
Okay, so thanks so much, everyone. I know that was a very quick session. I am going to be posting all our panelists' emails in the chat right now, and I'll leave this open just for a few more minutes, just so everyone can get that information. While I do that, is there any closing comments from any of our panelists?
Other than the fact that we appreciate the time and the shotgun approach at least gets some people thinking, but it's never enough time to dive into deep discussions such as Scott would like to get into, which Scott obviously contact us. We'd be more than happy to talk.
Same here. I didn't get many questions, but that would be great. I was willing to answer the, are we going to be fully automated anytime soon? But Tim and I would be like, we'll have to talk, right?
Mingu, any closing thoughts?
No, this was a wonderful. Thank you for Kathy and the team for your time and the audience as well. And I'll be happy to answer any questions offline.
Okay, sounds great. Thanks so much, everyone. So for all our attendees, feel free to join back at the main session. And thank you to all our panelists. Appreciate your time and the engagement from our attendees. Thanks again. Have a good day, everyone.